Hello, my geeslings. It's my pleasure to introduce another guest to the Robinsons podcast universe. Today, in this episode, I speak with Michael Harris, who's a mathematician at Columbia. I met Professor Harris when he gave a guest lecture in the philosophy department on computers in mathematics and automated theorem proving. He is a philosophically minded mathematician, which isn't always the case, or isn't often the case, or isn't really ever the case. But there are some exceptions like him, and he gave such a brilliant lecture that I immediately asked him if he'd be at all interested in talking on the show, and I was so happy that he was, and he was pretty enthusiastic about it. So Professor Harris did his undergraduate at Princeton. Then he got his PhD from Harvard, and he works in number theory, which is thought of as sort of the most prestigious branch of mathematics, and we talk a little bit about why that is. Among other things that we discuss, we talk about the tragic figure of Alexander Grothendieck, why mathematics is such an intrinsically human endeavor. We talk about beauty and creativity in mathematical practice, and whether computers will ever replace mathematicians and the role of computers in mathematics going forward. So as you might have figured from this introduction, this is a very mathematics-heavy episode, but I don't think we talk too much about supremely, technical developments or technical work. I think pretty much anybody can follow most of the material. And it's all pretty interesting, and I imagine that most people who aren't in a philosophy department have really thought much about it. And philosophy of mathematics is it's important to me, but it's not really a priority in most philosophy departments at all. So even if you are a philosopher, you probably don't know that much about it, because they don't teach courses on it too much. So anyway, I hope you enjoy this conversation. I really did, and I really hope to speak to Professor Harris more about this in the future. Enjoy. You were telling me about the tragic figure of Alexander
Grothendieck. Yes.
So I've heard that name so many times, obviously, because he's a big figure in mathematics. But who was he, and what did he do that was so important in particular?
Well, I suppose I can talk, since you mentioned that I refer to him as a tragic figure. He was born in 1928, I believe. His father was a Russian anarchist. His mother was German, and his father was named Shapiro. His mother, Grothendieck. The father went to fight. I guess both the parents went to fight in the Spanish Civil War. They were revolutionaries. The father eventually died in the concentration camps, and this son, Grothendieck, they were eventually he ended up. He and his mother both ended up in France, and he was protected along with other Jewish children by at a Protestant school in the south of France. Sometimes he had to hide in the woods. He became interested in mathematics. He rediscovered some important mathematical ideas on his own, and he got to talking to some of the major mathematicians of the day in and around Paris.
As a young person,
as a young person, and then he was discovered. The story goes that Laurent Schwartz, who was one of the first Fields medalists, Bourbaki member,
which is the most prestigious,
right at the time, yes,
yeah.
At night, it gave him a list of unsolved problems in the area, hoping that he would be able to make some progress on one of them, and within a few months he had solved them all.
Have you seen Good Will Hunting, by any chance?
Oh yes,
Yeah. So he strikes me off the bat as a character somewhat like Matt Damon's then.
Well, except that he did go through the established channels, and then very quickly he became he became a recognized professional mathematician. He had issues because he was stateless and he couldn't get a job, not having a French citizenship. And eventually they created the institute south of Paris for him and his projects. During the 1960s, he and an international group of leading algebraic geometers together revolutionized the field. And then at the end, he discovered that this institute was obtaining 5% of its financing from military sources. He protested. He was lifelong pacifist and anti-militarist, and in many respects exemplary activist. He resigned, and then he gradually, although he didn't completely give up mathematics, he moved away from mathematical life, and then became gradually more and more eccentric, and moved away from everything. Didn't want to talk to any of his former friends or students. All of this and he died in obscurity in a village in the Pyrenees. But the importance of his work, very briefly, that he introduced in a very systematic way the notion that mathematical objects are defined less by their intrinsic properties than by their relations to other objects of the same kind.
Of the same kind.
And this is the technical term is a category.
Oh, so then I did hear his name when I was reading about Alexander Voevodsky.
Not
Alexander Voevodsky, Vladimir Voevodsky.
Right.
Yes, but am I right? Is that where I would have heard his name?
Well, Voevodsky was one of the many mathematicians, I guess, 2 generations after, who built on Grothendieck's work. And
great.
One of his life projects, Grothendieck's life projects, was to develop the theory of motives. And the
motive cohomology.
Motivic cohomology was so. The motivic cohomology was I don't want to be too precise about this, but this was emphasized as an interpretation of Grothendieck's hypothetical theory of motives by Beilinson. So there's an intermediate generation who's now at the University of Chicago, and so one property, if there were theory of motives, then there would be motivic cohomology, and the motivic cohomology would motivate. That's the reason for the word, motivate the known cohomology, which are the topological properties of the objects of interest, which are the objects of algebraic geometry, solutions to systems of equations, of systems of polynomial equations. That's what algebraic geometry is about. And Voevodsky constructed motivic cohomology and proved many of its most important properties. That's why you would have heard of him.
Actually, I heard of him because of univalent foundations.
Right. So that was yes, but you would not have heard of univalent foundations if Voevodsky had not previously established his reputation for having created his version of motivic cohomology.
The reason that Voevodsky came to my mind, though, is you mentioned that Grothendieck was discovered, and when I was reading about Voevodsky, so I just went through the PhD application process, and it was very arduous, very time-consuming, and in philosophy, it's all about putting together one very polished piece of writing, and mine happened to be on Abraham Robinson. But Voevodsky didn't even apply to graduate school. His professor in Russia just made a call to Harvard, and they just let him in.
Oh, I know all about this because I was in Russia at the time, and I was reading a book, and Voevodsky came up to me and started. He was supposedly an undergraduate, although I don't know whether he was officially anything, and he started explaining to me what was in the book. When I was on an exchange with Russia. This is in 1989 at there was an mathematical institute of the Soviet Academy of Sciences, and I was on a 9-month exchange. I attended lectures in the seminar of Berlinson and people I just mentioned on motivic cohomology, and Vojevodsky was just one of the people in the seminar, and we got to know each other. And I think we had we had a fairly decent relation, because he was another tragic figure, I suppose you know, that he died very early, young. And he had to overcome some well, I guess addictions would be the...
Oh, really?
Yeah.
To what?
Well, I'm not sure how many things, but certainly he had a drinking problem.
Okay.
And he...
My vice is sweet food.
It's unlikely, but you could... you never know what's going to happen. He was a very charismatic and yet elusive figure in that sense, like Grothendieck. Maybe he didn't create a school, although Univalent Foundations to become a movement which he subsequently repudiated. He thought that the people who were developing it were not faithful to his ideas, in the same way that Grothendieck felt that the people who were developing algebraic geometry were not following his plan. That was one of his... He was bitter about that, and that's the subject of this two volume just collection of writings that just came out, unpublishable, but published nevertheless.
That's funny. Yeah, it strikes me though as fascinating that of all these fields, mathematicians are still discovered, and they, unlike I don't get the sense that philosophers are really discovered so much as they are trained. Mm-hmm. Whereas mathematicians, there is still this, I mean, there's only one Ramanujan, but there's a Ramanujan-like phenomenon where there are people like Grothendieck or Vojevodsky where they're just these brilliant flashes in the pan almost. So.
I think that, I'm not really sure about this. I think that Vojevodsky did go to the schools, the specialized schools, and he was already recognized. The reason he didn't register was that he was just not interested in formalities, and
as a lot of these eccentric, brilliant people are.
And but Grothendieck was definitely self-taught.
So, shifting toward you, how did you end up becoming a mathematician? I'm sure it's a very long story, but were you always very gifted at and interested in math?
I don't think so. How it's good that you use the word how rather than why, because I spent some time thinking about the why question and realized that it's endless and not and maybe not even well posed. But how is something I can answer. I had a high school teacher who encouraged me very, very much. He was teaching an experimental class in vector geometry, and I liked it. And he is in Philadelphia, and he encouraged me to apply to some summer programs. There was a famous summer program in Ohio, but my parents wouldn't let me go spend the summer away from them, so I went to the one at Temple University in Philadelphia. And then I was also interested in molecular biology, which was at that time very exciting. They were discovering the workings of DNA, how year by year major discoveries were being announced and people were getting Nobel Prizes. But when I went to Princeton as an undergraduate, I had a double major, but very quickly I dropped the molecular biology or biochemistry, as they called it, because the mathematics department was just so interesting.
Was it the best in the world then as well?
It's hard to say. It was.
Up there,
I'm sure it was certainly one of the best, and it continues to train leaders and to hire people who were dominant in one field or another. But it's there are other countries and there are other universities in the United States. There are areas in which Princeton is not particularly strong.
Mathematical logic, the one the philosophers like.
For example, yes,
Yeah.
Berkeley is bigger in mathematical logic than Princeton.
Yeah.
Although there was, when I was there, Dana Scott
He was.
and Simon
Okay.
Kuchin were both professors
And then
there.
Gödel probably was at the Institute for Advanced Studies.
You know, Gödel was still alive then, but not active as far as I could tell.
So you work on something called number theory,
Right.
which is thought of, at least by outsiders, as the most prestigious branch of mathematics, of which there are many. I mean, would you say, there's algebra, there's geometry, but there are all these sub-branches that most non-mathematicians don't realize are there. They think mathematics probably starts and ends with what they studied in high school, trigonometry, and then it gets harder and harder, calculus. What is number theory?
That's that's also a question that could spend.
What is the simple Wikipedia answer, not the deep philosophical answer?
I could say what it is historically. It develops around certain kinds of questions involving relations among whole numbers, and they tend to be algebraic relations. But then you can ask questions about, for example, important theme in number theory is the distribution of prime numbers.
Yes.
How many prime numbers there are in a given interval, for example. Are there infinitely many pairs of twin primes, like 3, 5, or 11, 13, two primes that differ by 2? That's an unsolved problem. The Goldbach conjecture.
It's such a simple problem.
It's very. Is it true that every even number bigger than 4 is the sum of two prime numbers? That's an open, unsolved problem from the 18th century. That's a problem about just addition, and it's of the multiplicative relation between the additive and multiplicative properties of whole numbers, which is what people learn when they learn arithmetic.
So they're very simple problems that somebody who's even maybe a second or a third grader could understand.
Absolutely.
But that people who have been trying to solve for 300 years.
On the other hand, the most typical problem in number theory is finding the number of solutions or characterizing the solutions to polynomial equations. And the most, for the longest time, the most intriguing of these questions was Fermat's last theorem, whether it's true that for any exponent bigger than 2, there are no solutions to the exponent n. There are no solutions to the equation x to the n plus y to the n equals e to the n, where x, y, and z are positive integers. And that was ultimately solved by Andrew Wiles in the early 1990s. And if I'm not mistaken, he was around 10 years old, maybe just maybe a little bit more when he first heard of this question. So yes, that's the kind of question that if you're a curious and bright 10-year-old, you can also understand.
And presumably one of the reasons that third graders, even though they could understand this problem, can't solve it, is that even though something can be phrased so simply, it requires very, very heavy tools from all sorts of branches of mathematics to solve it. And then a proof like Wiles might have taken 10 years to develop, and then 10 more years of arguing over it, and then finding a mistake. I think there was one mistake in his case.
Well, it was okay. It was not quite like that. There was a path to solving this problem was opened up in the mid-1980s with a discovery, just a very simple sort of discovery by a German mathematician named Frey. It was understood, interpreted by Frey, and then more precisely by Jean-Pierre Serre, who was described as Grothendieck's mentor, although I think they were more partners than anything else, and Ken Ribbett, who's a mathematician at Berkeley, that if Fermat's last theorem were not true, then there would be a contradiction to the Langlands program, which is the name of the area in which I've done much of my work, and I can maybe say something about that. And when that was, most people thought, on the one hand, this means that all of a sudden the Fermat's last theorem is not just a curiosity; it's closely related to one of the primary structures of modern number theory. But on the other hand, except for Wiles, very few people thought that they could use this observation to solve Fermat's last theorem, and Wiles went and did it ultimately with the last step in collaboration with his student Richard Taylor by establishing this very particular case of the Langlands program. And the result is, well, now we know Fermat's last theorem, that's done. But more importantly, for the continuation of number theory, it provided a new approach to the Langlands program, which has been exploited by dozens of people, and more proofs that would not of other problems that were not specifically related to Fermat's last theorem, but also of central importance in number theory, were developed by using these ideas that Wiles had, according to the story, he developed in his attic over the course of 7 years. And there was a mistake, the first version, which was rectified in his paper with Taylor.
So, of all of these branches of mathematics, what do you think is it that attracted you to number theory? Is it the simplicity of the problems? I mean, they're so stark. I mean, and they're so easily phraseable, and there's a sense that there must either be infinitely many pairs of twin primes or there aren't.
Well, I went to a program at Temple, and they talked about the sorts of things that one can understand when one is a high school student. And then I went back to my high school with Mr. Grant, my former teacher, whom I continue to see and who gave me independent study. And he talked about, that was what we talked about, number theory. But I was also interested in topology.
Which is?
Topology is the study of shapes.
And what makes it different from geometry then?
Well, the difference between topology and geometry is that geometry, as usually understood, also incorporates the notion of distance and scale, and topology is about the properties. It
takes place on a coordinate plane.
Not necessarily, but yes, okay. There are coordinates. It's not a coordinate plane, but you can introduce coordinates and then study how they affect the other aspects. Geometry is a natural setting for physics, because what is physics concerned with the measurement of relations between objects in the universe, and these relations are being measured. That provides coordinates. Topology you can also study physics through topology. Then there would be some sort of more qualitative relations among these objects, whatever they are. I was interested in topology also. The Möbius strip and the sorts of things that could appeal to a teenager. Why do they appeal to a teenager? That's the why question again. I'm not sure I would even know how to begin to ask that. Well, what happened was, when I was in my first year at Princeton, I spent the first semester learning the undergraduate program, not necessarily very well, but I was studying it, and I was doing all the exercises in the undergraduate required courses. And I wanted to take number theory in the second semester, and I had a teacher who was an instructor, who only stayed for a couple of years, named Walt Hill, and he taught the number theory course in the evening, and afterwards he would stay after class and answer my questions, because I had not really prepared well I studied quickly through the preliminary courses. He would answer my questions, and we would talk. This went on. There was, because in Princeton there's nothing to do. Maybe you've been there. So
I've never been there.
You've done as much by not going there as you would have.
It's a pretty campus to look at.
Absolutely.
I've seen a beautiful mind.
Oh yeah. It's a nice place to be. And then, once he got to talking, I don't remember in what connection, about the Weil conjectures. Well, the Weil conjectures were what Grothendieck. There were 4 of them. Grothendieck solved 3 of them, and the last one was done by his student Deligne in a dramatic and unexpected way. But at the time, the last one had not been solved, and Walt Tillix talked to me about he was a number theorist. The main mathematicians of the time, including Grothendieck, he was the one who told me about what Grothendieck had done. He had not yet withdrawn from mathematics. He was on the verge of withdrawing. And he told me that the Weil conjectures were originally formulated by André Weil after he had proved the first case of what can be considered the first case of the Weil conjecture. They have to do with solutions of equations over finite fields. So this is solutions of congruences. And the theorem that Weil had proved, one of his most important theorems, Weil being one of the leading mathematicians of the 20th century, was counting solutions to equations in 2 variables, in congruences in 2 variables, and the estimate of the number of solutions. And the estimate has to do with the topology of this equation, which in a sense is very hard to fathom, because these are finite sets, so they shouldn't have topology. But in fact, they had a way of interpreting this. And he, what struck me was that he had proved this and he proposed that it be proved in general by using Lefschetz fixed point formula. Now, Lefschetz fixed point formula has to do with transformations of topological spaces of geometric objects. Okay. And you can count the number of fixed points, let's say the points that are left in the same place after you apply this transformation, by using topology, algebraic topology. And Weil said he had done something like this. This was an interpretation of what he had done in the case of these equations in 2 variables. It's a one-dimensional problem. And he said, there should be the conjectures were that there should be a version of this for higher dimensional spaces, or higher dimensional spaces of congruences, which is what was the main project of Grothendieck, to construct this theory. It was, but when I heard that Weil had used topological methods, and Grothendieck had realized these topological methods to solve equations that left me at age 16 fascinated. And that was at that point I decided, in part because of that the realization that number theory could involve such methods, and in part because my number theory teacher was taking so much time with me, that led me in that direction. But even when I was a graduate student, my first year, I wasn't sure whether I wanted to go into topology or to number theory, but I was leaning to number theory, and that was what I chose.
As I listen to you, my mind is, I'm listening to you, but my mind is also drifting to other questions that I want to ask. I'm thinking about, I'm also thinking about philosophy, and what all of this revolves around, or what's coming out of our conversation for me, is just how much the questions I have center around sociology and psychology. Yeah. And what fascinates me about that is math is thought of as the most objective science, in a sense. And yet it's still driven by humans and your interests, so that your personal interests, you're somehow drawn to number theory, what these big figures like Grothendieck or Tarski or Hilbert, their programs and what they push. And
number theorists don't talk much about Tarski.
Right. I know that. Tarski is just the name that comes to my mind. Do they talk much about Hilbert other than his problems that he posed?
Sure. I mean, he was a universal mathematician. So
okay.
And
but so I'm obviously interested in math right now. That's why I'm talking to you about it. And for me, it started with, as a kid, probably 5 or 6, my dad writing algebra problems on pieces of paper for me because I was bugging him and he wanted me to work on them, and I got a huge kick out of solving them. Or I got a huge kick out of solving those like little Mensa books. And then, like you, you seemed to really get good at math in high school. Were you always good at math?
Well, I didn't know that I was good, particularly at math. I was in elementary school they had tests in addition, subtraction, multiplication. They had city tests. They were called city tests in Philadelphia, and I got addition, subtraction, and multiplication perfect. But I always missed 1 or 2 in division. They were speed tests, so I didn't think I was all that special in math.
We had this game where it was called Around the World in 2nd grade, where everybody would be sitting down at their tables, and one student would get up and he would go to the next student, and the professor or the teacher at that point, would hold up a multiplication flashcard. And then the first person who gave the answer correctly would move on to the next person. And I was the only person to go all the way around the room. And it was those little experiences that made me like math so much. And it's funny how a good teacher or something can push you in that direction. But in other ways, my questions touch on other psychological factors. So one hunch I have about why people are particularly interested in number theory is there's some aspect of beauty that they experience, almost like art, or probably very different from art, but there might be some similarities. And beauty is probably not the largest topic in the philosophy of mathematics, but it's something that is certainly spoken about. And I'm curious, what makes mathematics beautiful to you, or do you even experience it in those terms?
I rarely use the word, and because there's a history of use of the word beauty in mathematics, and people who read about mathematics often read Mathematician's Apology by G.H. Hardy, in which he said that beauty is the, I don't remember the exact quotation, but it's mathematics must be beautiful. Otherwise, there's no place for ugly mathematics. All right, and so a lot of literary people find that to be the manifesto of mathematics, the point. But beauty. He tries to explain what he means by beauty. And I've written. I wrote a long essay on that and where the idea of mathematics as beauty comes from.
Perfect.
This theme goes back to the 19th century, but I
imagine it goes back to the Greeks. Or
actually, not so much. Not so much. Okay. You can read it into what Aristotle or Plato wrote about mathematics, but that's maybe forcing the reading. The whole idea that art was about beauty only goes back to the 18th century systematically. Right. Although, of course, you also,
I imagine its central role was probably religious.
For example, Oh no, it has
or historical.
many different things were written about art. But the why do mathematicians say beauty is the objective? Because what's the alternative? Why are people doing it? Well, it might be useful, and Hardy talks about whether mathematics is useful, but that he particularly said that number theory was not useful, and he said that mathematics is something is useful in the sciences if it contributes to there's exploitation and oppression and things like that. So okay. I don't remember the exact.
Is that accurate though?
No, I mean he was a pacifist.
No, is it accurate to say, in a more colloquial understanding of the word useful, that number theory isn't useful, that it doesn't have applications?
Well, that's what he claimed, and then it turns out that number theory, since to get through cryptography, number theory is that, as I wrote, is the
central.
Is the wish I remembered what I wrote, but is the I had a nice expression. Can you stop this, or maybe I can?
Go ahead. Keep. You can look it up.
Yeah. Let me see what I wrote.
Yeah, we don't want to miss out on any nice expressions. This is the point where I narrate this beautiful day we have by Columbia.
Right.
Oh, you found it?
Yeah. Right. I wrote that it's the because you can't order things online, you can't pay for things online without using the crypto systems based on number theory. That it's the bedrock of modern shopping, and
that is good.
And that's the way.
Oh, so number theory underlies the blockchain.
Oh, the blockchain. Yeah, in fact, the blockchain also, but this is before blockchain.
Mining.
But it goes back before that. You have to encrypt your credit card information,
and that's all number theory.
That uses so that this doesn't get transmitted through the internet unencrypted. It has to, but at the other end, it has to be decrypted. You use public key cryptography, and that was invented in the late 1960s, early 1970s. The methods that are currently used. So yes, cryptography. When you say that the application is to allowing Amazon to drive small shops and bookstores out of business, is that so? Then
there is some oppression there.
Then what you mean by useful is a matter of contention. But anyway, so what I discuss in my book is that the three.
And what's your book called?
It's called Mathematics Without Apologies.
Oh, so it's
well, that was a
targeted at Hardy. It's a hit piece.
No, that was it took over several months. The editors were coming up with different possible titles, each one worse than the last.
What was your hope? Did you? Have
I was having a hard time finding. But this was I preferred the subtitle, but the subtitle maybe is more
portrait of a problematic vocation.
Yeah, but I was not so happy with the title, but precisely because it's not specifically there's one chapter that talks about Hardy, but the rest of it not particularly. But there's a chapter which I said not merely good, true, and beautiful, good being like useful, and what is the justification for mathematics? And I try to find other ways to explain why mathematics is justified, or spending one's life devoting one's life to mathematics is justified. What kind of activity it is, and I tried to turn the question around. I'd say, who are the people who are asking the mathematicians to justify their work and their existence, as opposed to doing something, like essential work. Of course,
right. As a philosopher, as a one-day philosopher, I get that often as well.
I had that. I talk about how philosophers address similar questions, and it was not particularly convincing.
You weren't able to convince yourself?
No. I found this was in Britain, of course, where you really have to crisp and write
yes.
about improving the lives of ordinary people.
That's what he writes it is?
Yeah, right.
I don't think many people are reading academic philosophy.
Right. No, but he had to write this for whatever evaluation of. They actually closed philosophy departments in Britain at one point when I was writing this, and I said that my argument, which only convinces those who want to be convinced, is that it's the fact that people are doing things because they enjoy it should not require justification. I mean, this calls into question.
That's music. That's making movies. That's all sorts of things.
Right. So then, and under the current organization of society, who makes the decisions and who is asking others to justify what they do? This is it's not. I don't know whether in a genuinely democratic organization of society, the question about doing mathematics, why one does mathematics, would be phrased in the same way. There is, but of course, somebody has to pay for other people to be mathematicians.
Maybe it should only be done in private universities.
Well, I've also written about these contradictions, and there's not a simple answer, because the people who contribute money to support mathematics have their own agendas. Like I started something when I was in Paris. I started something called the Paris-London Number Theory Seminar, which met once a year in each of the two capitals, because I had some extra grant money. I wanted to find something useful to do with it. And this was in 2005, I think it started. So it continued and continues today. It's become bigger. And when I went the last time, which was, I think, in 2016, I was sitting next to my colleague, Kevin Buzzard, who we may be discussing later. And he asked me, do you wonder who's paying for this? Because it had expanded beyond my very, very modest initial budget. I said, yes, this was at lunch. And he said, well, it's something called yeah, I mean, I'm forgetting this. Is it at Bristol? Well, ultimately it was GCHQ, which is the British equivalent of the NSA.
Oh,
right.
Interesting.
The Heilbronn Institute.
Okay.
The Heilbronn Institute is an institute at the University of Bristol, and it's quite a good institute.
And is that because something you were doing was leading back to cryptography?
No, it's that somebody in Britain managed to convince the Heilbronn Institute to fund these annual meetings, and that meant that it was getting money from GCHQ. In the United States, NSA was also sponsoring some mathematics, some research in pure mathematics, until the Snowden revelations, when it turned out that they had not managed to purchase goodwill on the part of mathematicians, and so this grant program seems to have been ended right after that. So
we have strayed a little bit from my question about beauty.
Beauty, yes, we haven't talked about beauty at all. Yes,
no.
because the beauty is so. If it's not, so, it's impossible to separate. I think talking about mathematics or the justification of mathematics for the sake of beauty.
That's an interesting remark in its own right.
From the alternatives, which were truth, which is the one that interests philosophers. That when you talked about objectivity, what makes how mathematics seems objective. I've turned that around. What other than mathematics would philosophers consider as a touchstone of objectivity?
It's going to depend on the philosopher that you're asking, doesn't it? But I would just like to say, well, for me, the world is the only objective thing. What's out there?
The world is all that is the case.
Yes,
and which
Wittgenstein,
is,
right?
Right, which is
or the totality of facts, or something like that.
Mm-hmm.
Are you a big Wittgenstein fan?
Well, I did read Wittgenstein when I was in graduate school a lot, and somehow I absorbed a lot, even without realizing it. Sometimes I find myself saying something, or with writing a sentence, and it turns out that it's been stolen from my reading of Wittgenstein. But yeah, Wittgenstein is also very frustrating because he doesn't actually answer any of the questions. He just
right. I'm one of the people who's frustrated by him.
Well, that's good. You should be frustrated. If you are not, then you're probably misreading.
Yeah,
you're reading too much into him. As far as the process of asking questions is my. Well, you were at my talk in philosophy that the purpose of philosophy is to the primary activity of philosophy is to show why all the other philosophers were wrong
and to disparage them.
Right. Well, not necessarily to disparage them.
There's a lot of disparaging involved.
All right. Well,
maybe not in print.
That's just what you call human nature. Where you disagree with people, and then you take some pleasure in that. But the fact that you should point out the mistakes of.
But it is, I mean, fascinating. I'm using the word fascinating a lot, but it's striking. But it's a striking distinction between philosophy and mathematics that philosophical programs are always failing on the left and right, whereas mathematics seems to be a much more steady progression, and that is also distinct from the natural sciences. But something that Chaim Gaifman, my professor in philosophy, likes to say is that there's no phlogiston in mathematics.
No, there are dead ends, but there
are dead ends, but there aren't points where we have to throw out everything that's been done for 200 years or something like that and start over.
Although, but there are revolutions in mathematics in which the previous perspectives are no longer taught. This Grothendieck led a kind of revolution in algebraic geometry, and so people who want to do algebraic geometry have to learn his point of view. Although there are even newer points of view, but that basically derive from that. Let me get back to beauty, though. So in my book I explain why truth is a problematic justification for mathematics.
And when you say that truth, when you speak of truth as a justification of mathematics, you mean that mathematics might be justified by our learning about number structures and just what there is.
Well, if people who don't know what mathematicians actually do can say that mathematics, this is the mathematicians are establishing objective, true statements about what it's about, whatever they're about, or whether they're about anything at all.
Whether there are infinitely many twin pairs of primes.
There are right. There's that's the kind of question that philosophers of mathematics, the most sensitive philosophers of mathematics, ask what can you say about the existence of something when you don't have a proof. They put some large number of zeros after one, and then say what is this pair of twin primes at this stage is. You can't make a statement if you don't know that there are that many pairs of twin primes, for example. But what is the nature of that philosophical status of such statements? But anyway, I deal with truth. I deal with utility as a relative to some priorities that are not necessarily universally shared, and that leaves beauty. And so mathematicians say, but I argue that when mathematicians say something beautiful, that means that it gives them pleasure.
Okay.
And so, pleasure, since Plato has been has been disparaged as a reason for doing anything. So can't really say it's for the sake of pleasure, and of course it can be abused as a justification. But that's what people mean, as far as I can tell, when they say beauty. And I give a little bit of the history of that in my book. So that's why I avoid using beauty as a justification. But when I write letters of recommendation for people's work, that's how you can tell what are the real true values of mathematicians.
Intuition.
It's you read what they write about people who, the job recommendation letters. Say this person deserves the job, or this paper deserves to be published because such and such. Well, there are, I think, sociologists really ought to have access to these private correspondence of journals and of mathematics departments to try to sort through and classify the use of language, find commonalities in different countries, different languages, see what really is the motivation for mathematicians. And there are, but usually the motivation is within. It's within the given discipline. Say such a person has established a new method which allows for a different perspective on the standard problems, the classic problems of the discipline. Well, that sounds self-referential. And so another way of looking at mathematics is as I rely on Alasdair MacIntyre as a tradition-oriented practice. I think that's what he calls it, tradition-oriented practice.
Mathematics.
Mathematics is a tradition. Well, it is something that people do, in other words. People will do it, and they do it in an organized way, and they do it following, conforming to certain traditions. So that sounds like a conservative justification for mathematics, and I guess MacIntyre has sometimes been characterized as a conservative philosopher. Also, he's appreciated, I think, by some Catholic theologians. Maybe that was one of his starting points. But but it can't be denied. Mathematics as a discipline preserves its nature. This is maybe a Spinoza a perspective on mathematics. It is something that's done, and it tends to persist in its essence, which is a word that that doesn't mean anything, but whatever
Philosophers like it.
Right. Some philosophers like it, and some philosophers hate it.
Freshman philosophy students like it.
Well, I guess it has a history, essence, and I think Spinoza maybe has the most rigorous, to the extent that this can be rigorous, the most rigorous approach to that.
So is one of the major points, though, that you're making, that beauty is hard to pin down, but it kind of amounts to pleasure?
When you ask people what they mean by beauty, and in most cases, they say, you can give characteristics. You can say, some symmetry, a naturalness, inevitability. This is Hardy has a three properties. That's also in here.
Three properties that are beauty.
Right. It's well, I'm trying to figure out the...
No, you can...
No,
I'll continue narrating the beauty of the day. We've got some lofty clouds and blue skies.
Right. Hard to define. Beauty may be very hard to define, but he expects his readers to know what he means by art and to agree that beauty is one of its criteria.
Interesting.
Yeah.
I don't think that everybody would agree with that. There's a lot of ugly art.
Absolutely. I say that just around the time that that Hardy was writing, beauty was being exercised from the by the art theorists of art, including people from Hardy's circle. In fact,
when was he writing?
He was writing. Well, he was active. He wrote Mathematician's Apology around 1940. But he was active before that. And why did he get? The other question is, where does he get his notion of beauty? Well, he was one of the Cambridge Apostles, and the Cambridge Apostles were strongly influenced by G.E. Moore, who placed aesthetics as the highest goal. Let me see if I can find. Let's see, Mordell. Right. Unexpectedness, inevitability, and economy. Those are the three. Those are his three.
Could you repeat them?
Unexpectedness, inevitability, and economy. So I said naturalness and
economy.
Economy.
I see that.
And then Mordell, who was Hardy's successor at Cambridge in the chair that he held, added simplicity of enunciation. And I said, with that, it's only a slight exaggeration to say that the theorizing of mathematical beauty on internal structural grounds comes to an end. That's only a slight exaggeration. There was also a school of thought, neuropsychology, that says that the beauty of mathematics is related to other forms of beauty, and that it stimulates a certain part of the brain. And Michael Atiyah was an important British mathematician. Actually worked with this guy Samir Zaki. Do I have that?
I like the simplicity of enunciation.
Right.
That sort of goes back to what I mentioned earlier about the attraction of number theory being they're problems that everybody can understand, and we can understand what it would mean to solve them, and yet they're so challenging to solve.
Well, that comes back to what I hesitate to call human nature, because what I was thinking today is that before you talk about one of the problems in talking about what makes mathematics valuable is that there's no generally agreed definition of mathematics. There are attempts to define mathematics, and there are ways to define mathematics that leave people out completely, so that machines can, in some future, not necessarily too distant future, mathematics will be exclusively the province of machines, because they'll be faster and therefore better than human beings. And that's a vision that a lot of my colleagues share.
Is that this is an inevitability or
there are
desirability?
A lot of people. Some people consider it desirable, some people don't, but many very distinguished mathematicians are saying this. Others say this makes no sense, and I'm in the my perspective.
I'm in the this makes no sense category.
I'm trying to explain why it makes no sense, but it's not so.
I don't know if I heard it from you or if I came of this by my own accord. Either are possible, and you'll let me know afterward. But it seems entirely possible that computers could do mathematics that humans couldn't, because there are limitations to what we can compute. But the role, or the point, one of the points of doing mathematics isn't just to compile some compendium of Pythagorean theorems and just a body of equations and facts, but it's the mathematician's drive to understand, one, and just having a computer run and come up with this compendium doesn't involve any understanding on the mathematician's part, but it's also the thrill of solving puzzles. And that's, what got me into mathematics was solving those puzzles that my dad gave me, or in the Mensa books, or the flashcards. And that's the role of the mathematician that won't go away.
What I I've defined, or not defined, but characterized mathematics as a way of being human. Well, that leaves out machines. It's one of the ways.
Like
it's one of the ways that humanity has developed for being human, and I also would define it not as a relation among human beings before it is a body of work, or before it is a body of statements.
That's so exemplary of the gulf, though, between the mathematician and the non-mathematician, in that for you, mathematics is about being human, but for the non-mathematician who looks at it from the outside, mathematics is the province of computers and their calculators, and they have no interest in doing math because the calculator will do it for them.
Well, you know, also this has to be placed in a broader context of the economic context, development of industry and investment. You know, there's no return. There's no return on practice that leads to human enjoyment unless it can be monetized. So, and how do you monetize it? Well, you have to capture the market, and so that's why it seems to me that's what Silicon Valley is very, very good at doing. That's why they think mathematics is the sort of thing that can be monetized, like other aspects of human relations. And you know, it's possible that friendship, for example, that you think that's one of the characteristic behaviors of human beings. Well, friendship, if it can be captured by Facebook, so that you can only be friends through their Facebook platform, you know, that's well, then they extract a profit from that. So there's a drive to extract profit from all human activities, and why not mathematics as well?
When you say friendship, though, what comes to my mind is I came in here, and well, when I arrived at your office, you were deep in a phone call with a friend of yours, right, who I'm assuming was in a different country. And yes, doing mathematics. And right, that's part of the humanity that mathematics brings. It right, creates relationships. He's basically your hunting companion from 20,000 years ago, except now you guys are solving math problems instead of herding cattle or hunting cattle or something.
Right. Well, this is, you know, it's perfectly legitimate to argue, if you're a philosopher, that humanity has an expiration date, and human activities have an expiration date. There are certain examples of industries that no longer interest many people. Jaron Lanier talks about buggy whips. Apparently, a lot of people in California talk about how it's natural for Silicon Valley to replace existing industries because, you know, things become obsolete, like buggy whips, and, you know, mathematics could be one of those. But if you think of mathematics as a relation among human beings, then that's that's a very limiting way of imagining the future of mathematics. And I've been trying. That's why I have this Substack newsletter to develop arguments that will discourage my colleagues. I don't hold out much hope for a lot of computer scientists, because computer scientists have some vested interest in taking over mathematics, and I certainly don't hold out much hope for converting Silicon Valley engineers. But I would like my mathematical colleagues to stop thinking about the replacement of human beings by machines, say arguing that, you know, AlphaGo or Deep Blue or whatever is a model for the future of mathematics, because, you know, it's an analogy, but it's an analogy only if you think of mathematics as oriented to a certain kind of goal, as opposed to a way of being human. And this way of being human is a very powerful way of putting it. You know, there are a lot different people do different things, right? That's what makes life interesting.
So in line with this way of being human, well, first, we're at an hour and 3 minutes, and I want to be conscious of your time. Do you have time for one more push of inquiry? So in line with mathematics as a way of being human, what role, and this is another huge question, what role does creativity play for you in mathematics? Again, another big question, but creativity, spontaneity, those I think are huge aspects of being human. That's part of the whole puzzle solving. If the puzzles came with instructions and there was no creativity, we wouldn't be doing mathematics. It would be fodder for the computers. But there's something about the thought process, the dreaming about mathematics that makes it so ingratiating, or I don't know if that's the right. I don't think that's the right word. But
gratifying.
Gratifying, yeah.
Well, that's that question is impossible for me to answer because I'm not sure I have any meaningful sense of creativity. If I were to try to define if I were to try to define it objectively, as the what happens between two states where something is in the second state and it isn't in the first state, well, then that would narrow it down. But what's involved in that? I've had experiences in which I've didn't know something, and then a few minutes later I did, and is that psychology? Is there any other way to approach that than psychology? Is there a way? You can develop mathematical models. You can, I suppose, there are philosophers of creativity, although I haven't read anything especially convincing about creativity. Let me say, let me answer a different question that you didn't ask. Something I realized, I sometimes find myself rereading passages from my book or other things that I've written with pleasure because I think, this is a really clever sentence, or
I know the feeling. I'm more often horrified by what I read.
Well, that happens sometimes too. That happens quite often. But then, on the other hand, I do not find myself rereading my mathematical papers for the same. I sometimes reread them to try to figure out what I was thinking at the time, or how such a calculation goes. But I do not reread them for aesthetic purposes, for contemplation, or once something is done, there's a period of elation if I feel that I've solved a problem that I was wondering about for a long time, or a problem that other people were wondering about. A realization that these things, this connection, this relation of ideas works. But then it has to go in another, has to continue, has to go beyond that, because every mathematical document is partial. It's a stage in this process. What does it say on my door? Mathematics is a long conversation. That was my thesis advisor likes to say that, Barry Mazur. That was a conference I helped to organize for his 80th birthday. And mathematics is a long conversation. And long conversations. What is the point of a long conversation? What is the goal? What is the, you can, if your long conversation is on Twitter, then maybe Twitter is getting some money out of it. But if you have a long conversation, it's not. The goal is not defined objectively. There's no need to objectify it. So creativity is not. So I have written about my experience. Because I was mystified that I found myself beginning to think about and finding a part of a solution to a problem that was not one of my problems. It was a problem on the edge of my awareness. That's how my first substantial contribution to the Langlands program, which happened in the middle of my career after I'd been doing other things for a while. And I wrote about it in this book, and it's I eventually decided that it was an expression of or the working out of some adolescent jealousy. I was jealous of some of my colleagues, of my predecessors, and I was thinking unconsciously about the ideas that they had developed, that I hadn't, and then I somehow, in a dream, literally in a dream, I saw a connection that I hadn't.
That was the next and last question I was going to ask. This is just a matter of personal curiosity, but how or even do dreams play any role in your mathematical practice?
This was a dramatic incident because it changed the direction of my work, and it led within a few years to a solution of an important problem in the Langlands program, and it came literally through a dream that I had after attending a lecture. In the dream I put things together. That happened only once.
Okay.
I've also had dreams that which mathematicians gave me advice. Real people I knew who appeared to me in my dreams and told me I should do things in such and such a way, and but that never led anywhere. There is the famous example that I wrote up of Thomason and Trobaugh. Thomason had his friend give him the missing piece of her program that he gave that was wrong, but he could see that how to fix it.
But right, so in this dream, his friend gave him the wrong information, but it contributed immediately to his finding the actual solution.
Right.
Yeah.
Mm-hmm. I think it's not so common. People do. There are several important texts on the role of the unconscious in mathematical discovery.
Oh, really?
There's so the two maybe most often quoted are there's Poincaré. Poincaré discovered the relation between his geometry, non-Euclidean geometry, and what are called now automorphic functions. It's one kind of automorphic function. He discovered this while climbing onto the omnibus.
Yeah, I read this in high school.
And so I learned this, relatively late. And he wrote about it, and his analysis was that the unconscious is you're thinking about a problem. Your unconscious continues to think about it, and then it finds the solution, and it informs you of it. So a lot of the work is being done unconsciously. And then there is a more developed version of this in Adamar's The Psychology of Mathematical Invention. More examples. But, the reason I wrote up my experience was that it was unlike the example that Poincaré gave, or the benzene ring, or some other famous examples. This was something I had not.
Who was the benzene ring? Because I think I read that.
Kekulé.
Okay.
And
was that he was like sleeping in front of a fire or something like that?
He saw these different atoms dancing around in a circle
in a fire.
Yeah, but then there's some question as to whether he made this up after the fact.
Nice story to make up. Okay. Well, thank you so much for doing this with me.
Well, thank you. It was. I haven't. Maybe I'm not going to watch it because it's been painless so far, and if I watch it, that may not be.
Great. I'm glad to hear it. Well, hopefully, maybe once the. Well, I guess if it wasn't painless, there's nothing that you have to forget. So maybe in a year or so, once you've forgotten about this one, we can do it again. So.
All right. Well, maybe in a year I'll look at it and then
Great.
I'll shudder.
All right. Thanks. I have recorded this about 10 times because I'm just so bad at asking for help. But if you could subscribe, comment on whatever medium you're consuming this nascent fledgling podcast on, that would be so helpful, because the best thing for helping me grow this podcast at this point is making it at least appear that I have an audience. So thank you for listening, and thank you for supporting me.